So, hello everyone. It's my great pleasure to present the talk about understanding and steering language models for financial reasoning. Uh, Recently, we have been doing a lot of works that works with the reasoning of language models, and uh, we'll present some exciting findings and also uh, discuss some hypotheses and some intuitions. So, reasoning has been a great focus area for large language models. Uh, in many of the uh, recently released language models, in either the title or the first sentence of the paragraph of the announcement, the large language model service providers will mention the name, will mention the capability reasoning. So in O3, the first sentence says O3 is our most powerful reasoning models that pushes the frontier. In R1, reasoning is in the name, the title of the announcement, and also the reasoning is in the name of the model, and R stands for reasoning. Gemini as well. In Gemini 2.5, they mention reasoning in the first sentence. Well, in the newest version of Gemini, they said just the artificial general intelligence, and the reasoning is considered part of the general intelligence. Command A reasoning as well. And for anthropics models, they also mention a lot about reasoning. They are really good at coding, and coding is a form of reasoning that is at the same time very complex, but also relatively deterministic to evaluate. So we have seen apparently reasoning has been an area that people value a lot when developing the frontiers of large language models. And it actually also has a lot of applications in our daily lives. With the reasoning capabilities, the language models could be prompted to make plans, for example, before the trips, or uh, allocating the activities under the scheduling constraints, or figuring out the solutions to problems and go from what we know to what we do not know. The reasoning capabilities can be used to analyze the numbers. And for financial problems, there are a lot of numbers, the uh, the tables, and they are usually scattered across multiple documents and websites. So with the ability to reason, and of course the ability to understand the numbers and go across multiple documents, the language models could be used to be very helpful automators for part of our analysis procedure. Of course, for the learning and research settings, the language models reasoning capabilities are very important as well. So in the for example, the presentation of the finance reports, there are a lot of new concepts to the readers, and the reasoning capabilities could be used to generate personalized explanations of the new concept, so that there will be a lot wider population to use the financial technologies, and the reasoning models could be used to suggest new ideas for uh, the uh, that about the financial products, and allow the human users to make the eventual decisions. So we have seen that the reasoning capabilities could be used to do a lot of things, but there are still some limitations. And here is a very uh, prominent reasoning failure. It's called sycophantic behavior. Uh, the sycophantic behavior is essentially that when the human users prompt the models to uh, to do something, effectively the human gives an instruction and the model follows the instruction. And for many of the time, the model follows exactly the instruction. But uh, the problem of sycophantic behavior is that the models follow the instructions too well. Sometimes the instructions are incorrect, or sometimes the instructions uh, it might not be the most benefit for the human users, or it might not be the most financially profitable for the user to exactly follow the instructions. But yet, the model will still tend to exactly follow the instructions and uh, uh, following uh, the intricate details and also following the emotions or following the attitudes. Uh, so uh, there are a lot of examples that illustrate this kind of sycophantic behavior. And when that happens, even if you say something that are, for example, incorrect or not having the most benefit to the potential stakeholders, the model will still agree with you and follows the 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 reasoning procedures, which in that case they appear to be helpful, but this helpfulness could be adversarial. Here's another example about the improvement areas of reasoning. This is about the counterfactuals. So the reasoning procedure allows the models to connect the problems to the common senses. The common senses are those facts that do not appear in the context. So, uh, with the common senses, the models could answer those kind of questions like, does hydrogen appear in the ocean? And inside the reasoning chain, we can figure out an abstract structure of the common sense reasoning, going from the uh, hydrogen to the ocean. So with this kind of architectures, we can connect the concepts with structured reasoning graphs with deterministic syntaxes. If this kind of graph can be formed, then we can say that this answer will be a yes. And with this structure, it is also possible to extend to counterfactual scenarios. So in this example, we can uh, make counterfactual perturbation in two ways. We can perturb the part of, or we can perturb the spatial. So if we perturb partial, hydrogen, effectively we are imagining a counterfactual world where hydrogen is not part of water. And when that happens, we cannot deterministically say that hydrogen appears in the ocean because the ocean is full of water, but hydrogen in that world would not be part of the water. Another way of perturbation is perturb the spatial relation. So in that case, hydrogen is part of water, but water is not in the ocean. Something else might be in the ocean, but we do not know based on uh, this counterfactual setting. So we also cannot directly answer and say that hydrogen appears in the ocean, following this common sense reasoning tree. We found that when we make this kind of counterfactual perturbations, the state-of-the-art language models struggle a lot when uh, following this structural reasoning tree. Apparently, they are still heavily relying on their existing common sense without adapting to the new scenarios, especially when the new scenario has some conflict with the uh, common senses that are stored inside the model's memory. Another reasoning failure involves overthinking. So nowadays, we want the language model-based agents to work on complex problems that require a lot of steps. And these steps usually start with a thinking stage. And after that, the model comes up with a planning. Uh, with the plan usually goes like the plan usually leads to an step-by-step instruction for itself. After the planning, the model would follow the plan and go out in the real environment to make the actions. So the workflow would look like think, plan, act. But a lot of people realize that the workflow usually can sometimes go like this: think, plan, and then it goes back to thinking, and then figures out a new plan, and then it goes back to thinking again. So the model thinks and plans for unnecessarily long before the model actually goes out into the real world to the real environment to act. So people call this overthinking. So this overthinking trend appears not only in the software engineering, but also in the common sense reasoning, math reasoning, and a lot of other types of reasoning problems. So it seems like many models just want to be uh, questioning itself and continuous thinking, even if the model already knows the answer. So uh, we hypothesize that the solution towards improving those reasoning problems of the models exist inside the models themselves. So there are two intuitions that supports this intuitions, that support this claim. First, uh, the models are huge. So there are a lot of parameters, which means that among those parameters, it is likely that there exists some steering wheels. And second, recently there have been some promising progress for finding out those steering wheels, but the actual form of those steering wheels remain open. So let me uh, illustrate how large the neural networks are with the numbers. So people currently they are talking about uh, the model sizes in terms of billions, but uh, without illustration, it's hard to imagine how large is 1 billion. So let me use this illustration. Uh, Imagine the volume of a bottle of Coke is 1. Imagine a luggage case. There are around 2,000 uh, unit of volume there. And imagine a basketball court filled with luggage cases and stack them up with uh, 10 or stack them up with 100 layers of luggage cases. Then the number would be around 10 to the power of 8. But this is still not 1 billion yet. We need to consider 10 such basketball courts. And now we have 1 billion unit of volumes. So this is the size of the parameters inside a neural network. And this is not even the among the largest neural network currently. This is actually among the smaller uh, LLMs. So there are a lot of parameters out there, and likely there will be some sort of parameters that could control the behavior of the large language model. Actually, we have seen some promising illustrations of how the subset of the uh, deep neural networks parameters and the representations that are computed by those parameters are informative. So this is a quite interesting work that uses the technological probe to find the relevant information. So we find some testing results from the intermediate representations and then use those probing results. We are able to predict the fine-tuning or post-training performance of the language model with very high accuracy, just using a linear regression model. So the representations of the neural networks are informative, and it can predict many things. So if the representation is informative, probably it can tell us something about the reasoning behavior and perhaps when to stop the reasoning. So this is another recent work we we put the uh, representations onto a two-dimensional space, and we look at where the representations demonstrate some anomalies. So on the right-hand side, we see that token 64 is an anomaly, and on the uh, actual model output, the token 64 is but. So this at this token is exactly the place where the model starts to overthink. Before this token, the model already knows the answer. 1 plus 2 should be 3. It already correctly answers the question. But starting from this token, the model starts to question itself and continues with inefficient reasoning. Additionally, inside the other layers of the model, with the logic lens verbalization, we realize that the model is uh, starting to think about stopping or waiting. So this offers us a signal. So if we observe this kind of signals and stop the reasoning procedure here, then the overall reasoning effect, uh, the reasoning behavior might be more efficient, and we are able to a large extent maintain the original reasoning accuracies while reducing the tokens consumed. There is another type of steering wheel. It's called the sparse autoencoders. Sparse autoencoder features are recombinations of the representation's individual dimensions. But there are a lot of sparse autoencoder features. We figured out methods to find the correct steering wheels, the correct sparse autoencoder features. And in this work, we realized that if we choose the sparse autoencoder feature correctly, then it's possible to make the model safer while at the same time preventing the model from becoming too stupid. So there is usually a concern about the trade-off between safety and uh, general model performance. So when the safety scores go up, the general intelligence performance could go down. But with the proper choice, with the proper algorithms to choose the SAE features, it's possible to strike a good balance between the safety performance and the general intelligence performance. Now, there is another intuition about the steering wheels. Uh, the form of the steering wheels remains open. So we believe that there is no fixed form of the steering wheels specific to the actual type of problems. So the form is some people also say the word granularity to describe the forms. So the steering wheel could appear in the granularity of a layer or the component within a layer. For example, an MLP or a layer norm or one of the attention head. Or some people also say that some neurons or the forms of a subset of the model weights appear to be the steering wheels. And we also have seen that the sparse-oriented encoder features can also be successful steering wheels. But I would say that it remains unknown what the most appropriate analysis granularity is before we actually go out to test those different granularities for each problem. So a lot of uh, analysis should be done to find the most appropriate granularity, particular to the problem. And recently, there is also a possibility to go beyond one granularity. For example, in this work, we find the structure called sheaf. So sheaf essentially is a combination of the weight granularity and uh, the neuron granularity. So uh, we the intuition was that we first try to find the subset of the neural network. The neural network is a computation graph, and when we keep only like 1% of the computation edge and nodes, it is essentially keeping the 1% of the weight and the connections between the model weights. Then uh, the model's behavior could be largely unchanged, but it could be 99% lighter. And then we went one step further. We went inside the weight and we further discarded 90% of the weights uh, inside the remaining parameters. So we further discarded around 90% of the remaining weight and realized that the model's behavior still remained unchanged, largely unchanged. So uh, in this way, the remaining sheaf seems to be the the steering wheel, and uh, the the small percentage of computation graph could essentially explain why the model has that eventual output. Uh, because when we get rid of the other part of the model, the model's output still remain unchanged. So if we want to steer the model behavior, we should steer on this uh, crucial uh, model subset. And this model subset appears to be a different granularity from the previous fixed granularity settings. Another potential new forms of steering wheel is appears in the mixture of expert models. Nowadays, many models have the ensemble of experts. So the for each task, uh, perhaps the the router inside the models assigns some particular experts to the for that particular type of problem. So there was the traditional intuition that the 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 experts specialized well. But what we observed recently was that there is no one-to-one domain expert mapping for those different type of tasks. Instead, there is a to some extent standing committee of experts that handles that are activated for many of the problems in the tasks, and there are also some sort of experts that are activated only in uh, the particular domains. So uh, this leads to some potential new opportunities for the steering wheels. Perhaps we could steer on the experts level as well, uh, or to during the training procedure encourage those experts to encourage some experts to specialize and encourage some other experts uh, to continue with their role of the standing committee. So uh, nowadays we can also go outside of the model. We can the steering wheel could perhaps appear in the agent's memory or tools, or uh, or either the persona settings. So the steering wheel does not need to appear inside the model's parameter. The the model's prompt could also be considered the a part of the agent, and uh, there might also be some benefit because the prompts are human readable. So we can design the memories in some smart ways so that uh, the uh, target, the long-term target, the short-term target, and the uh, base that the agent is making decisions based on, uh, they could potentially be be adapted and they could be controlled by the human users. So uh, this this intuition has actually been helpful when building up the AI agents for trading. So uh, with the promising progress, we still have a lot of open problems. For example, what is the most suitable form of the steering wheels to control the models, and how to make the controlling effective and efficient. So we don't want to uh, combinatorially search for all of the possibilities of the steering wheels. We want to very quickly find one steering wheel and find a good steering wheel. And also we want to find the steering wheels that are useful not only on one problem but also in many other types of domains. So we want the steering wheels to be generalizable. Uh, I think in the next few years, people will discover more about the uh, steering wheels of the large language models and also perhaps the uh, large vision language models in the context of the AI agents. So yeah, these are the talk. Now I'm open to questions.